I'm guessing, but people there, I guess they're doing, let's say, E's or something like that. Oh. Down like 90% during the day. All right. Do a quick review, kind of see where we're going. We're gonna be finishing up chapter 8 today. Always good to review because we're getting closer and closer and closer to our final. Okay. Matter of fact, before we get done class today, we'll go over the calendar real quick to kind of see where we're going. Your project has opened up. I'm going to go over that with you a little bit today because you're going to notice as we get into 10.1 today, a lot of that project is going to be open up for you. That way you can kind of understand it a little bit better. Okay. Remember 8.1. Okay. Estimating population means. What's important about that? What did you learn in 8.1? What was known in 8.1? Huh? They gave you something in it. Yeah, they gave you the standard deviation. It's known. And that standard deviation is specifically the population standard deviation. So because everybody wants to get an a good way to kind of remember, how do I know? Okay. Well, what you're going to have to realize is they're going to be wanting a confidence interval. And when you're reading it, just make sure that it says, okay, confidence interval, it's going to give you some information. But then that standard deviation it gives you is going to be the population standard deviation. Okay. From there, we went to 8.2. 8.2 is not going to be on your final because 8.2 is a tool that we're going to use for 8.3. Okay. 8.3, we use that student's T distribution because once again, we're finding a mean again, right? But what's important now? In 8.3, we don't know what anymore.
Standard deviation.
But we're given one. But what is it? Think about it. You have a standard deviation in 8.3. Is it the population standard deviation? No, remember they'll tell you it's the sample standard. So they read almost, they're very similar in how they're going to be read. I want a confidence interval. Okay, the mean of the population, or the mean is this, because remember, the mean of the sample is what we consider to still be the mean. That's going to be our point estimate, right? Okay, but then you just got to read it real carefully because when they're not going to always say sample standard deviation. They may say something like, we got all this data, yada, 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 and here is the sample mean, and here's the standard deviation. Notice they did not specifically say population standard deviation. Okay. They kind of lumped that in with the sample part. So you know you're dealing with a sample mean in that. Okay. So you know that whenever you start doing your error and stuff like that, you're going to have to use that student's T distribution. Okay. Trying to give you these little things to look for whenever you're taking your final because my questions aren't in order. Okay. They're randomized. Okay. And then we got into 8.4. 8.4, we're dealing with proportions. What's a good way to know you're dealing with proportions other than the fact the question might actually say the word proportion? What is something you can go, I'm dealing with proportions in this one?
4 more decimals, right?
That's rounding. Percentage, yeah. You see that percent symbol, you're like, oh, I'm dealing with proportions in this one. I know where I'm going to, I know what. It may not help completely and go, man, we did that in 8.4. What were we doing? Okay. Kind of help you out a little bit. Okay. Now, let's go in here now. Our point estimate, remember for proportions, is that p-value, that p-hat value. That's what you're plus and minusing from. Give you a whole bunch of formulas. Okay. So once again, let's go back to 8.1. Does anybody remember the calculator button that you could use for 8.1 instead of having to deal with the big formula? Huh? You're close. Who said Z? Z interval. Exactly. Very good. It's Z. You might want to write that down because remember, you get a note card. Okay. You can put that on your note card. So for 8.1, you're going to be using that Z interval if you choose to. Now there is that formula where you have to use that critical value table that you have in the very front of your book. Remember that critical values of Z where it says, hey, you have a 95% confidence interval. You look up the number, that's a number, and then it's going to be a formula of standard deviation, population standard deviation over the square root of n. You plus or minus that from your point estimate. Either way you want to do it. Okay. Some people are more comfortable with formulas. You will be given all the formulas. Okay, so don't think you right now you have to start memorizing. I'm going to give you the list of formulas. I'll be emailing those formulas to the professors who are in the other locations. There you go. But I don't tell you what they are. You still gotta go, huh? What am I gonna do with this guy? Okay. Well, let's continue on. You kind of got an idea for that one, Z interval. 8.2, you didn't get anything. That was all a concept, teaching you about how we get the student's t distribution. 8.3, though, what will be the calculator button for that one? Think about it. If 8.1, we're using a Z interval, very good. For 8.3, you would use a T interval. It's literally, if you look on your calculator right now, you can go to Z interval. The next one is going to be a T interval. Okay? And it'll work on there. And then the last one, 8.4. What is it? Anybody remembers it? It's a weird one. Nope.
Invite.
Nope. Inverse T is whenever you're trying to find it. When they give you the area first and you just 1 minus, you were close, 1 minus prop, did you say this prop Z?
No.
Okay, I'm sorry, I guess I didn't understand. 1 minus prop Z interval, okay? If you start looking on your calculator right now, if you start scrolling, the first one you're gonna get to is 1 minus prop Z test, okay? Keep scrolling. And you'll get to prop Z interval. We will be using prop Z test, okay? Don't need to mix them up. They're doing two totally, matter of fact, what we're gonna get into today is the testing, okay? Very good with that so far? Probably a good idea to practice that calculator work before the final, okay? Just so you can make sure you're getting valid answers, okay? Good so far? Looking over some of y'all's chapter tests, just kind of looking at them, just be careful with your rounding. Okay, that's the hardest thing right now, just the rounding and stuff like that. So overall, it seems like everybody's doing pretty good though. So today, estimating population variance. Okay, you need your book for this one because you can't use your calculator. There is no calculator work. If you don't have your book, I will show you. I do have a chart downloaded. And I didn't fix the pin button. So, estimating population variance. If I gave you this, hopefully everybody in here could go, I can find the variance of that because my calculator is going to do the work for me, isn't it? Okay. So General Auto is testing the variance in the lengths of its windshield wiper blades. A sample of 12 windshield wiper blades is randomly selected, and the following lengths are measured in inches. Okay. Gives us all that information up there. Now let's remember kind of some review again. How would I find the variance of all that? Easily. It's either that or you go back to 3.1 and do it all in your as a big formula, right? Or wouldn't I just use the what? Just give me where would you go to? What would it look like?
List.
Yeah, just go to your list. Right? Put all that information down in your list and it's going to give you everything. Well, will it? What does it give you? It gives you the standard deviation, doesn't it? It doesn't give you a variance. So how do you get variance? Square it, okay? So doing the math for you real quick, notice if you look this up, it talks about population. So it says the population variance is 0.22. Well, to get my variance, obviously I'm going to square that number. Now remember, and where probably some of your rounding problems is this one, technically speaking, if you want me to be like honest about this, you should just go to right here. You should just be going to the tenths. Isn't that where everything went to? Okay. I went to the hundredths. So really, in essence, I should just be using that number right there. Okay. So now think about it. Whenever I do this, whenever I do the next one, the variance, I'm going to square that number. You don't want to square that 0.2. You always want to go one past it, right? And then you do your squaring and then you round from there. Always calculate to one past the decimal place of the desired place value. So on this one, though, if you did that, the only problem with that, if you didn't go 2 decimal places, you get like, well, you could get 0.1. But I'm going to give this to you as just 2 decimal places. But that would be taking this number and squaring it. Everybody's good with that, right? That's your new point estimate. Okay, for variance, when dealing with variance or standard deviation, okay? And it's literally going to be, the whole question is going to be focused on, I'm looking for the variance or variability of this thing. What do we think the population is? We don't have the actual standard deviation. We don't actually have the actual variance. So what we're going to do is what we've done before. We're finding a confidence interval, and this is where the possible population variance or standard deviation is, okay? Now, there is no button on your calculator. And things are going to get a little murky here for a little bit, but don't worry. You're going to have to actually do some math today. Okay, it's not as bad as what it looks. But you're going to learn about a new distribution. Okay? This distribution is called chi-squared. This looks, okay, it looks like x squared. Okay? But it's called chi. That's the capital letter chi. X is chi. So we call it chi-squared distribution. And yes, once again, it does follow along with some very simple rules that we need to remember. The chi-square distribution is a continuous probability distribution that is completely defined by its degrees of freedom. And these properties are true. The chi-square distribution is skewed to the right. Remember what that looks like? That's something where the trough is on the right-hand side. The values of chi-square are always greater than or equal to 0. The shape of the chi-square distribution is completely determined by its number of degrees of freedom. As the numbers of degrees of freedom, or remember what that is, degrees of freedom is the sample size minus 1, exactly. So as those, the more samples you take, the more it's going to approximate a normal curve. That's all it's saying, okay? The mean of the distribution is equal to the number of degrees of freedom. So degrees of freedom is the mean. The variance is equal to 2 times the degrees of freedom. Okay, so, and I can't think of anywhere, maybe in your Hawks, maybe in Hawks, they might ask you that question. On your final, I don't ask you for anything like that. Okay, doesn't mean you won't need it for your homework. Okay, so everybody good with that? Kind of, that's just kind of word salad. Now let's see what it looks like. That is a chi-square. Okay. Notice it starts at 0. That's important. Okay. It doesn't shoot off to infinity on the left-hand side. Okay, it starts at 0. Now, over here on the right-hand side, it does shoot off to infinity. There is an asymptote there, an x asymptote. Okay. To look this up on your chart that you have in your book, it literally says right here, the critical value for x squared distribution with a degree of freedom of 5. So we look up 5 right here. This tells us the area here. So you're literally just doing what you did earlier. Come down, find the intersection point, and that gives you that 1.145. Okay, and that's how you're going to use your chart. Good so far, pretty straightforward. Okay. Here's where it changes. We're still taking area. Okay. And what it's saying, by the way, is like a very low, and I'm going to draw on this one, on a very low degree of freedom, like really low, like 1 and very little, you might have something that looks like this. Okay, and kind of do that. But let's say we got a degree of freedom of like 1,000. Well, that's going to turn into that. It would still be starting at 0, but notice as your degrees of freedom, that wave kind of moves. And it'll start approximating the normal curve. That's what this is saying. So far, so good. Kind of understand chi-square a little bit. Okay. I want you to notice a few things about it, though. That's very important. It's not symmetrical. So you can't come in here and start thinking of it the way you did earlier, like with normal curves. Okay. You can't go, well, if I get this score here, I've got the same score over here. Well, let's be honest. You see where that line's at, and that line is saying from right there, that chi-square line, 95% of that curve is filled in. Well, if I went symmetrical with that and put another line right here, can we all agree that is not 95% there either? You know, that would not be the same score. So that's why you gotta be careful. This is why we need a chart for it. You have a couple of formulas you're actually gonna need to know these. They're gonna be on your, like I said, I'll give them to you, but you're gonna need to know them. There's one. That is for variance. We're gonna dissect the whole thing. I'm just showing you the formulas right now, but I'm gonna go in here and dissect the whole thing, especially this guy right here and this guy right there. I'll show y'all what they do, okay? Those are the reasons for your charts. If that's for variance, how would I get standard deviation from that? Square root, exactly. So notice if I wanted the standard deviation, all it is square rooting, okay? So if you know one, you got both, right? If you did standard deviation, you just do what? Square it. Now, before we get into the actual math of this, let me tell you where they're going to trick you. Okay? So kind of save you a little bit of trouble. They're going to be saying something like, we're looking for the population variance, da 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 da. Okay? And then at the very bottom of it, they're going to give you the standard deviation. But the problem is the question wants what? The variance. So they may try to switch things up on you. They may be asking for variance and then give you a standard deviation, or they may want standard deviation and give you a variance. Just be careful, okay? Sometimes they'll say, here's your variance, sample variance. This is what we're looking for the population. It's cool. They've kind of kept everything, you know, congealed or the same. Make sense? Okay, so just kind of watch out for that. Sometimes they'll throw those little curveballs at you a little bit. Now, let's go back up really quickly here. And I'm going to show you how to use your chart, what they're saying here. Okay. Matter of fact, I'll just go to the next slide and we'll do it down below. Procedure for constructing a confidence interval for a population variance or standard deviation. Find your point estimate. Okay. Either you're going to have to put it into your list function or they're going to give it to you. Okay. If they're asking for variance, but they give you standard deviation, make sure to square it. If they ask for standard deviation, but they give you the variance, make sure to take the square root of it. Okay. Based on the level of confidence given, calculate your alpha over 2 and your 1 minus alpha over 2, and then use your table and then substitute. But what does all that mean? Let's do an example. A commercial bakery is testing the variance, okay, in the weights of cookies it produces. A random sample of 15 cookies is chosen. The weights of the cookies are measured in grams and found to have a variance of 3.4. Build a 95% confidence interval for the variance of the weights in all cookies produced by the company. Okay. Let's go through with what we know and then I'll get into the formula. Okay. We do have an N value. That's our number of samples, right? N is going to equal 15. We also know degrees of freedom is defined by what? N minus 1, which is easy enough. That's just going to be a 14. Okay. Do they give us a variance? Yeah, what is, how would you write variance? Good to know, because I'm on, if you see things, a bunch of symbols. Go back to what I did at the very first class. Population is always what? Greek. Samples are always what? Variables. So what is gonna be your variable? How would you write sample variance?
Square.
Very good. S squared, that's your sample variance. And they give us a sample variance of 3.4. And then they always give us that confidence interval. Okay, everything is based off confidence intervals now. How confident do we want to be? Okay. Our confidence interval is 95%. And now we have all the information we need. Okay, now let's look at what we're gonna have to deal with. We're gonna have to deal with this little formula here of n minus 1 s squared all over this chi-squared alpha over 2. I know I'm dealing with variance because did you see the word standard deviation in there anywhere? Did it ask for standard deviation? No. Everything is based off variance right now. So I know that this is the formula I'm looking at. Most of that you got. N minus 1, you got that. Isn't n minus 1, that's just your degrees of freedom, right? That's the definition of it. Okay, we've got our sample variance. Okay, but that x, that chi-squared alpha over 2, well, what is that? It's easier than what you think. We got to calculate those. Okay, notice they give us a confidence interval, right, of 95%. So watch this. 1 minus 0.95 is going to equal 0.05. Divide that by 2, and you get what? 0.025. Okay, that 0.025, if you go back in time, wouldn't that been like your z alpha over 2? Yeah, remember where you found that? Okay, or your t. Okay, well, look at this. This chi-squared alpha over 2 is going to equal chi-squared 0.025. And that's going to equal something. I don't know what yet. Because I've got to use my chart. But I need to calculate one more thing. Don't I have this guy over here? I've got that 1 minus alpha over 2. So for this one over here, I've got this chi-squared 1 minus alpha over 2, which is equal to this chi-squared 1 minus 0.025. Which is equal to chi-squared 0.975. Now, if you would permit me, I'm going to back off of this screen and I'm going to pull up the chart. The same chart that you'd be seeing in your book right now, or that you will have on your final. Right here. We know our degrees of freedom was 14. Okay, so we kind of close up just a little bit. Already, yes, perfect. You know our degrees of freedom was 14. I have two numbers I'm looking for. I'm looking for, and we'll just have to use you just have to kind of remember your notes. I have a chi-squared of alpha over 2 of 0.025. If you look up at the very, very top, look at the area. And if you go all the way to the end almost, it has 0.025 up there. And when you go down to 14, you should be seeing 26.119. That's going to be the number you're looking for. Okay? But you have another one. You have that 1 minus. Okay? Which that one was 0.975. Well, notice you have that on the left-hand side. Left-hand side, I see that 0.975 up here at the top here. When I scroll down all the way to the 14, Notice I get that 5.629. There's your numbers. That's what you have to look up. Are you good with that? Let's go back to the PowerPoint. So when I come in here, knowing what I know now, I know that this part right here is going to be 26.119. My other number is going to be 5.629. And now I have everything I need. I have to put everything into the formula. So let's come this direction with it. N minus 1 is obviously going to be the 14. Then I got this 3.4. All divided by 26.119. Same thing in the numerator again, so it makes it kind of nice. All divided by now the 5.629. When you do the math to that, you can put it down here, very bottom, you get 1.8 and 8.5. Either one of those answers. So what that is saying conceptually, do you know the actual variance? No. You do not know the population variance. The population variance is a fixed number that you don't know for a fact. But by the calculations you just did, you can say with a confidence level of 95% that if you took 100 samples or did 100 tests, 95 of them would contain the actual variance. It would fit in between those numbers. Okay. Yeah, honestly, I don't like variance all that much because I would have taken the standard deviation of it, and then I would understand the weight's a little bit better. It's hard to understand weights when they've squared them. Okay, but still, that's exactly what it's telling you right now. You have found this variance. Okay, and the larger the numbers of gaps, there's a larger variance. Okay, it's kind of the swing. Okay, variability. Think of the word variability. Okay. Good on that one? Now, showing you how to find that, okay, your level of confidence interval for variance. Because these are not symmetrical, we also cannot use the normal way of finding a minimum sample size. So once again, in your book, okay, they're going to give you another chart. Okay, here I have it on the PowerPoint screen. You're going to have to use that chart to find the minimum sample size. So let's look at it. And it's mind-numbingly easy. A market researcher wants to estimate the standard deviation of home prices in a metropolitan area in the Northeast. She needs to be, hear that word, 99% confident. I'm going to underline that because that seems like it's going to be important, that her sample standard deviation is within 5% of the true population standard deviation. Assuming that home prices in that area are normally distributed, was the minimum number of home prices she must acquire? Use the tables given previously. Well, let's look at the tables they're going to give you. Notice this is what it looks like. Minimum sample size for estimating standard deviation. Hey, what would you do if they gave you variance? Square root it. Yeah. Because notice this isn't a table for a variance, this is a table for standard deviation. Okay. So just kind of be careful about that. So notice it's literally just you go in here and go, okay, well, standard deviation was within 5%. Well, look, it says right here, S is sample standard deviation, is within this percentage of the value of the population standard deviation. Well, isn't that the number I'm looking for, that 5% there, right? And then they say what? How confident, 95 or 99? 99, so there's my 99. So it looks to me, there's your minimum sample size right there. That's it. You just kind of just do that on a chart again. Okay. If they'd have said 95, you'd have gone 769. If they'd have said 99 or they'd have said 20%, you just scroll down. Okay, just kind of keep using this chart. Okay. Pretty straightforward on that one. In a given sample of 136 pipes, the average diameter was found to be 3.94 inches with a variance of 0.264. Sorry, 0.26. Give a point estimate for the population variance of the diameter of the pipes. Round your answer to 2 decimal places if necessary. Hey, when dealing with population variance, what is our point estimate? Huh?
The mean?
When we were dealing with 8.1, our point estimate was the mean, right? In 8.3, our point estimate was also the mean. Only difference is whether we knew the standard deviation or not. 8.4, our point estimate was what? That p hat value, right? So what's now going to be my standard deviation? What's now going to be my point estimate? That right there. It's just going to be your sample variance. So notice all you're going to be putting there, very simple, is going to be that 0.26. Your unbiased estimator, your point estimate when looking for variance is the variance. Okay, so just kind of remember that. Because if you're using the formula, that's what you got a plus and minus from. Except on this one, you don't have an error because it's not symmetrical. We can't do that. That's how come we have the other one. Do this one. You got your book, try to work it out. Look up your table. You don't have your book, sit next to somebody that has their book. Okay, see if y'all can't figure it out. I will write out the formula for you. Okay? Good thing to know is, am I looking for the variance or am I looking for standard deviation? Variance. So we don't have to take the square root of anything, right? Okay. If you want me to, what I can do is you'll give yourself I'll give you about a minute to write down the information you need. And then I'll pull up my chart that I got up here, so you can use the chart up on the screen. Everybody good? Can I click over the chart or do you want me to give you a minute for a second? Switch back over just so you know. So I feel good. Those numbers. How about that?
Got 1.37 for the lower endpoint, and I
Did
got
you round up? 1.37. What was your thousandths place?
1.37, 1.
These are one.
I got 1.38.
What'd you get on yours? For the thousandths place? We did on mine first.
1.34.
Well, you'd round down. At 4, you'd round down. 1.384. Oh, you did? Let me see. Hold on. 18, 2.22. Divided by 28.869. Yep, 1.38. Don't trust him. Right here.
I forgot to add, what is it?
No excuses. You're in math class.
I did 2.2 instead of 2.22. That's the difference.
Yes, it does matter, doesn't it? It makes you feel any better if you're off by like literally a hundredths on this one, like on your final. I'll go in there and look at it and be like, I'm gonna give you points on that. Okay, so. I am definitely not trying to fail you. I'm only half trying to fail you, I promise. No. Okay, how do you feel about that one? I mean, it's kind of messy, isn't it? I mean, but overall, it's not the hardest math you ever done. You've all taken college algebra. Okay. So it's just gonna be remembered to, know how to use your chart. And to be honest, what I remember from taking the statistics class, the hardest part was just remembering when do I got to do what? And that's what you gotta remember is how to pick and choose when to do. When do I need to know to use the z-score? When do I need to use the t-score, the critical t-value? When do I need to do variance? When do and so that's what I'm trying to tell you now. Look for these specific words, and then out of that, start kind of parsing out the information, okay? And that's only gonna come with doing enough in the practice, okay, on your homework. So you can't get by without practice, okay? Good. Okay, let's jump into 10-1. We're not gonna finish 10-1 today.
What was the last one we just did? 8.
That was 8.5. We're skipping 9. Okay, so we're jumping to 10-1 now. 2 seconds. I'm gonna pull up y'all's Canvas page very quickly, so that way before class is over with, I can go over your project with you. Alrighty. Fundamentals of hypothesis testing. Okay. This is gonna work the same way as we've done already. I'm gonna teach you the concept. And then guess how you're gonna do it? You're gonna learn how to do hypothesis testing when you have the mean, when sigma's known. Then you're gonna do a hypothesis test when what? Sigma's not known. And then you're gonna do a hypothesis test with proportions. And then you're gonna learn how to do a hypothesis testing with what? Variance or standard deviation, right? So notice it kind of goes exactly the same way you just learned things. I give you the concept, and then we deal with these 4 separate kind of scenarios that we may need to decide to do. In this first one, it's kind of a broad overview, okay, over everything, and then we'll get into the nuts and bolts of everything, okay? So what is it? The fundamentals of hypothesis testing. You're gonna hear this a lot, okay? Any science people gonna be in the sciences later on? Like you're kind of like looking at that later on, like believe it or not, even like law, they're using a lot of this now. Okay, so law and like even depends on how far up you go in education, they use a lot of this, they call them p-values later on. Okay, look at this. A hypothesis is a theory or premise. Often it is a claim that someone is making that must be investigated. In science, a hypothesis is usually a claim about how the world works. In statistics, a hypothesis involves a claim about a numerical value of a population parameter, such as the population mean, proportion, or variance. Okay? That would be like me saying, I believe, okay, that 33% of my math students are going to fail. Now, once again, it's subjective, right? Remember that word? But that's my hypothesis. I believe this, X, Y, Z, okay? Now, usually I'm backing that up by looking at some data. I don't just kind of like just willy-nilly like walk through the park, you know, and go, this is my number. No, it's usually because we've looked at data, okay? Like this right here, this is data, what I have up on the screen here. This is so weird watching that thing. When I turn away, it scans away. Because it doesn't see my face anymore because of the camera, so it's like. Notice right here, data time spent using social media. I could make some hypotheses out of this. I could start coming in here and going, what do I think about what I'm seeing? Okay, and I want you to look at that one, kind of maybe come up with it yourself. Go, what would you like to infer? Because remember, that's really what you're in right now. Before chapter 8, we were more in descriptive statistics. You were getting data, you were figuring things out, and you were describing what you saw. But now what we really are is we're in inferential statistics, where we're saying we've got data, we don't know anything about the population enough to give concrete numbers, but we can infer this. Like I could come in here and take all these times, couldn't I? Put them into my list function, and I could get a standard deviation. And I can say how much variability is there probably in the population compared to this graph here. Or couldn't I look at the percentages and look at the proportions of times? Or any one of a number of things. I can look at the mean of things. And then I can infer something about the population from what I learned about the sample. Okay? Remember, that's a hypothesis. I would be thinking this, right? So that's kind of where we're going with this. Now, hypothesis testing is a statistical process for determining the likelihood that a given hypothesis is true. Now, this is how you're going to do it, okay? Procedure, performing a hypothesis test. 1, you're going to state the null and the alternative hypothesis. It's a lot easier than what you think. I'll be honest. This one took me forever to wrap my head around, and when it did, I was like, oh, I felt like, duh, okay? But it is kind of one of the harder things to see, okay? Then, determine which distribution to use for the test statistic and state the level of significance, okay? Gather data and calculate the necessary sample statistics, and then draw a conclusion and interpret the decision. Okay. Here's what's happening. Last semester, I had the students do a project. First off, they decided what they wanted to study and they went out and gathered data. And then we went through the whole semester. About every 4 weeks, we would play with our data, see what it was doing. But to be honest, if it was a true statistical class, like if it was a master's level class, we did it wrong. Because you should never gather data first. Okay? What this is telling you is this, is like if you want to do a statistical study, it doesn't matter, even if you wanted to do something random in your home or whatever, you were around your friends, you're seeing something happen in the real world that you decide, I'm going to challenge that common belief or whatever, suggested belief. And so then you go, I'm going to make a hypothesis that either, if this is wrong, okay, that it's either greater, less than, or not equal to that number. That's kind of how you're gonna have to do it, okay? And then you turn around. Are you gonna look at the mean? Notice what it says in number 2, determine which distribution. Are we looking at the mean? Okay, do we know the population standard deviation or do you not? So notice you can go either way with that. Are you looking at the proportions? Are you looking at variance? Which test statistic are you gonna use? And then after that, we come in there, then you go gather your data. Okay, and then do the math and then draw a conclusion. And the reason for that, prevent from chapter 2, prevent bias. You don't want to start gathering data first and then look at it and then draw a hypothesis, because then you're being controlled by what? Your data, not what you thought. Okay, now, if you're not careful, you draw a conclusion, you got to be careful how you draw your data, because if I say, hey, I create a drug and I want to make sure it works. Well, I know it only works on him, I'm only going to look at people like him. Now, you got to be simple random samples, do proper statistical methods, okay? So, there's our methods. So, step 1, state the null and alternative hypothesis. Okay, this is going to be the hardest part probably for you. And that's what you're going to be doing this whole time, okay? The alternative hypothesis, H of A, H subscript alpha, is a mathematical statement that describes a population parameter. And it is the hypothesis that the researcher is aiming to gather evidence to support. It is also referred to as the research hypothesis, okay? This right here, okay, that is the belief you are challenging. The null hypothesis, denoted by H subscript 0 or with, okay, H of naught, okay, or H sub naught, is the statement that expresses the value currently believed to be true. It will always be a statement of equality. You need to remember that. Always. Okay, this is the commonly held belief, okay, or the common belief. So when you're reading your question, it's going to say something like, everybody thinks this. That's your null. Because it's something everyone believes. But you believe, there's your alternative. Okay, or so-and-so believes, or whatever. They're going to say something else that's going to say, I don't agree with that. So there comes the hypothesis. Look at this one I've got beneath here. Scroll up where you can see a little better. Let's face it, many of us consume too much added sugar. Adults, young adults, and children in the U.S. consume, on average, 17 teaspoons of added sugar every day, more than 2 to 3 times the recommended amount for men and women, respectively. Okay, this adds up to around 60 pounds of added sugar consumed annually. That's 6 10-pound bowling balls. okay, of sugar. And that's an actual study. That's a real study. You know how much 17 grams of sugar is? A Dr. Pepper. One Dr. Pepper. Okay, and actually a Dr. Pepper has like 45 grams, so add on some more to that. Okay, so the commonly held belief is this. Notice the H of naught, H of zero. That's your null. Okay, here we're dealing with a mean. Okay, it didn't say anything about variance. It doesn't have a proportion. It's going to be the mean. So I'm going to put mean. Our null hypothesis, our null hypothesis is always an equal statement. Always. Okay. So this will always be written as equal. Okay, but equal to what? Well, how about 60 pounds? And we go on 60 pounds of sugar. So the commonly held belief is this, that the average person consumes what? 60 pounds of sugar. That's it. That's what it tells me. But you have an alternative hypothesis. You say, I don't believe that. Now, it doesn't tell you greater than, less than. I'm not going to sit here and go, I think it's less. Because I'll be honest, if I was doing this test, I think it's more. I watch people. I have seen you people eat in the cafeteria. Okay? See me eat in the cafeteria. Okay? You know how much healthy food has sugar in it? It's amazing. Go look it up sometime. Like the more healthy it is, the more sugar they add to it. Because they use sugar as a preservative. And healthy stuff tastes like crap. So what do? Add sugar into it. Okay? So my H of alpha is still going to be the mu. But then this. Not equal to 60 pounds. Do not think every time you put equal, it's going to be not equal to. Okay? Sometimes it's going to be less than. Sometimes it's going to be greater than. Okay? For this one, it's going to be not equal to. You're going to need to remember these not equal to. Okay? Because later on, they're going to become very, very important. So the belief that I'm challenging is this. Scientists believe that we consume about 60 grams of sugar, added sugar a year. I don't think so. I don't think it's equal to that. Okay? Now, I'm not saying it's greater than or less than, but I don't believe that. And that's what I'm putting down there. Okay? And then that's how you're going to do this homework. You have to go in there and decide, what are they saying? First off, here's a little hint, kind of help you out. These will always be the same. These will always be the same. That will always be equals. So if you can figure out all that, that's the only guy right there that you got to really think about. And to be honest, a lot of times on your test, we give you all of that already. Okay, I already give you the mu, I already give you the equal, and I already give you what it's equal to. But then you got to go, oh, okay, am I using a less than, greater than, or not equal to? Okay, can I help you out a little bit? Okay. Let's do this one, and then we're going to call it a day today. So that way we don't get too far ahead, because I'm going to have to go through this very quickly for the people that are those taking their SAT tests. Determine the null and alternative hypothesis for the following scenario. And I want you to try, and then I'll play catch up. Okay, so after learning that Pete Colott of Switzerland could hold his breath for 19 minutes and 21 seconds underwater, a group of students decided to conduct their science fair project around the amount of time the average adult can hold their breath. Sounds to me like a mean, doesn't it? Notice I'm kind of picking things out automatically. Part of the group found the research to suggest that adults can hold their breath for 30 seconds when submerged in lukewarm water. The other half of the group found evidence to suggest that the mean time is different if the water temperature is colder. The group would like to test the claim about adults holding their breath in cold water. Okay? I'll give you about a minute. You write down whatever you think it is. I need to know the null, which is always written as H of 0. And then I need to know the H of alpha, which is my alternative, okay? What is the common belief? And then what is the alternative that I am proposing or they are proposing? Could we all agree we're dealing with a mean? Well, if I'm dealing with a mean in one, what am I dealing with the alternative? A mean again, okay? My null always has to be what type of statement? Equal, it's always gonna be. Okay, so what is my mean equal to? 30 what? 30 seconds. Okay, so what's your alternative hypothesis? Greater than, less than, or not equal to? Not equal to what? Exactly. Once again, it has to be 30 seconds. Your mean has to be equal to something. It has to be an equality statement because if you put anything other than an equality statement, you are now trying to prove for them. Okay, that's how come it's always an equality statement. It doesn't even matter if they say a commonly held belief is that people can hold their breath for greater than 30 seconds. That doesn't matter. Your mean will still be equal to in that statement. Because if you don't put it equal to, you're now having to prove their statement and then turn around and try to prove yours. That's not how science works. You don't prove the commonly held belief. It's up to them to prove the commonly held belief. You're proving your hypothesis. Now, hear me out, and it's gonna be said again before we get out here, and I may just show you the project, so don't forget. You're proving nothing. You don't know any truth about this at all. Okay? You're just saying there's a statistical probability that what I'm saying is correct. Doesn't mean you're 100%. No, you could be 100% wrong. But you're going on a statistical, I believe this is gonna be statistically true. Statistically valid. Okay. Now, let me show you a project real quick. Has anybody looked at it yet? Good. Then you go into your model page, go down to your class. Here. Model, go down to your project. You have two choices. You can do one or two. Now, mind you, some of these you can find online. I have found as many as I could, and I have put in some fake information. If I see my fake information on your paper, you get a 0. You know what my fake information is? Now, I don't mind you working together, but you can't use your calculator. You have to do everything by hand. Okay, everything. Come here. Let's just look at, y'all want to look at tennis or travel? You got a choice of either one of them. Tennis, let's look at tennis. What does it look like here? The Hawkeye electronic system is used in tennis to display the instant replay that shows whether a ball is in bounds so players can challenge calls made by the referees. Assume 611 challenges and 172 of them were successful with the call overturned. Use a 0.01 significant level of test to claim that the test was at least 1/3 of the challenges were successful. And then you have to start filling out all this information. What's the claim? What's the hypothesis? What is the sample statistic? What is the test statistic? What is the critical value? Translate the critical value to a proportion. What is the alpha? What is the p-value? You'll learn about p-value in the next class. Draw a graph labeling the test statistic, critical values, mean, p-values, and critical values. Label any values of the horizontal axis as both standard random variables and proportions. What is your decision? Write out a full sentence and use the expression of null or alternative hypothesis without defining what situation they stand for in the problem, and is it possible you made an error? Okay. If so, what could cause that, and what type of error would it have been? You'll learn about errors in 10.1 as well. Okay. But there is a lot of this you've already done. Okay? You've learned about sample statistics. You've learned about test statistics. Remember Z, T, proportion, what kind of test statistics you're using. To see an example, look at this one. This example will help you understand the expected level of detail.